Hi, I'm Mark Barsamian. In this video, I'll be discussing analyzing the sign behavior of functions and using what we know about the sign behavior of functions to solve inequalities. This material is in the book section 2.3, Continuity. More specifically, the relevant reading is from the bottom of page 123 to the top of page 126, examples 4 and 5. And the relevant homework is homework 21, solving inequalities. So in calculus, it turns out that an important tool in analyzing functions is to determine where they are positive, negative, zero, or discontinuous. And this could generally just be lumped under the heading of determining the sign behavior of a function. Some of the tools that we will use were used in a previous video, the video for homework 19. They were these general continuity principles that basically if you have two functions that are continuous, you build a new function using those continuous functions, the new function that you get is also continuous, except possibly at x values that cause the denominator to be 0. And then there was this giant theorem 1, general continuity properties of some particular kinds of functions. The most useful or the most frequently used part of this theorem was C and D, that polynomial functions are continuous for all x values and that rational functions are continuous at all x values except for those x values that make the denominator 0. Let's make some observations about sign behavior of functions. From the previous video, we observed that a function that's continuous can only change sign by touching the axis and crossing it. At those x values, there's an x-intercept. We had this kind of thing in the previous video. We had a number line, and we had some important x values, and we knew some sign behavior on the intervals between those x values. We knew that on those two green intervals, the function was positive, had positive y values. And we knew that on those blue intervals, the function had negative x values. Well, since the function was continuous, we knew that the only way that the function could go from having positive y values to negative y values was to touch the x-axis and cross it. So we knew that there had to be x-intercepts at these three x values. That's encapsulated in this theorem in the book, Theorem 2, about sign properties. If you have a function that's known to be continuous, and if the function does not equal 0 anywhere on some interval, then either the function is going to have positive y values for the whole interval, or it's going to have negative y values for the whole interval. But a function that's not always continuous can also change sign by jumping across the x-axis at an x value where the function is discontinuous. At these x values, there's not an x-intercept. So consider a graph like this one. So this function has a jump at x equals 5, so that's a place where the function is not continuous, and it has a vertical asymptote at x equals 10. That's another place where the function is not continuous. And we see that the function changes sign at those x values. The function changes from positive to negative, back to positive, without ever having an x-intercept. So based on these observations, we realize that to determine the sign of a function, it's helpful to first determine the x values where the function has an x-intercept or is discontinuous. And we'll give those kinds of x values a name. We'll call them partition numbers. So a partition number for a function f is an x value where f is discontinuous or where f of x equals 0. So on the intervals between the partition numbers, the sign of the function f does not change. Now keep in mind that a function does not necessarily change sign at every partition number. For example, consider this function. So notice that there are partition numbers at x equals 5, 10, 15, 20. X equals 5 and x equals 10 are our partition numbers because at those x values, the y value is 0. X equals 15 and x equals 20 are partition numbers because at those x values, f is discontinuous. There's a jump at 15 and there's a vertical asymptote at 20. But notice the function only changes sign at 5 and 15. So again, a function does not necessarily change sign at every partition number. But if you're looking for the x values where a function might change sign, the only candidates are the x values that are partition numbers for f. So with this terminology of partition numbers, we can articulate a procedure for determining the sign behavior of a function using what's called a sign chart. Here's the procedure from the book. Find the partition numbers, step 1. Plot the numbers, the partition numbers, on a real number line, which divides the number line into intervals. Select a test number in each open interval in between the partition numbers, and then finally determine whether the function is positive or negative in each interval. Now, a couple of things I would change about this procedure. We don't really need to do 4. What I'm going to call the sign chart is the number line thing that we draw and we annotate with plus and minus signs. There is something that I would add to this procedure. Notice this procedure only tells you to put information about the behavior of f in the intervals between the partition numbers. But I think it's also helpful to indicate the behavior of f at the partition numbers. That's, for one thing, it's easy because we find the partition numbers by finding places where f does something. Either the y value is 0 or f is discontinuous. So we've got this information, so might as well put it on the sign chart. Also, that information is useful later when we use the sign chart to do other things. We'll study 4 examples involving determining the sign behavior of a function by analyzing the formula, and then using the sign behavior to solve inequalities. Our first example is this one. Let f of x be this polynomial function. Now here's the standard form. Well, so our first job is to find the partition numbers. Step 1 is to find all the partition numbers of the function. Now remember what partition numbers are. Partition numbers are x values where the function is discontinuous or where the y value is 0. Now remember something else. Polynomial functions are continuous for all x values. So step 1, find partition numbers. So we observe that f is a polynomial, so there are no x values that cause f to be discontinuous. So what we need to do is solve the equation f of x equals 0 to find x values that cause x to be 0. So I'm going to turn this around. Now the solutions to this equation are x equals 3, x equals 7. So those are our partition numbers. So that's step 1. Let's go up to step 2. We have to plot the numbers found in step 1 on a number line. So here's our number line. Now remember my addition to the book's procedure. I said also indicate the behavior of f of x at each partition number. So I'm going to add that here. I'm going to say f parentheses 7 equals 0. And I'm going to say f parentheses 3 equals 0. Now let's go see what step 3 is. Step 3 is to select a test number in each open interval and evaluate f of x at each test number. So let's find test numbers. That just means sample x values. So there are my sample x values, my test numbers. So we just have to find how f behaves at those sample x values. So we have to find f of 2, f of 4, and f of 6. Now, we're going to be substituting in x values into the function f of x. It's easiest to use the factored form. I've mentioned this in previous videos. When you're substituting in particular x values into a function, it's much easier to use the factored form. And also, when you're trying to solve the equation f of x equals 0, it's much easier to use the factored form of the function. So we'll use the factored form to find f of 2. Now, here we could multiply these numbers out. 9 times -1 times -5 would give us plus 45. But really all we care about is whether the result is positive or negative or 0. Well, we know it's not going to be 0 because this is not a partition number. So we just need to indicate whether this result is going to be positive or negative. We can say positive because the product of two negative numbers is positive. Now we compute f of 4. And the result is that that product is negative. It would be the number -27, but we don't care about the size of the number. We just care about the sign of the number. And I've made a mistake over here. My sample number needs to be to the right of 7, so I need to use x equals 8. Now, notice we have the behavior at particular test numbers, sample numbers, in each of these intervals. But remember that the function can't change sign in those intervals. So if we know the sign of the function at a particular test value, a sample number in an interval, we know the sign of the function on the whole interval. So we can indicate that in a number of ways. I think what the book does is they put little pluses or minuses across the whole interval. So I'm going to take this plus sign, or this positive, and I'm going to use it to put pluses on a whole interval. So that indicates that that entire interval is one in which the y values are greater than 0. So there's the sign behavior on all the intervals. Now that's our step 3. Finding the sign of the function at each test number. Now remember, that's as far as I go. I don't do step 4. I call this thing that we just built the sign chart. I say that this thing is the sign chart. Now there's one more thing that I would add to the instructions for the sign chart. Here I would say title the sign chart. So this may sound unnecessary, but you want to say that it's a sign chart for f of x and give the formula for the function. Later in the course, we're going to have situations where we have sign charts for a bunch of different functions involved in a particular problem. So it's going to be very important that if you have a diagram, you title it. You tell the reader and you remind yourself what this diagram is for. All right, so there's the sign behavior of f. We've done question A. Now let's go to question B. Solve the inequality f of x greater than 0 and present the solution set 3 ways: a picture using a number line, interval notation, and set notation. Now in the book, you're only asked to do this middle one. But I think it's important to be able to do all 3 of these, partly because in order to come up with the solution to this inequality, it helps to visualize something using a picture. So making a picture using the number line is a helpful thing to do. So we're supposed to find the x values where the y value is greater than 0. If you go up to our diagram, you can see that those x values are out here and out here. So our picture using a number line could be this. So we color the part of the number line that is the solution set. So the x values that are green are the ones that are in the solution set. And notice that I have open circles at 3 and 7 because x equals 3 and x equals 7 are places where the y values are not greater than 0, so they should not be included in the set. Now, how do we present this solution set using interval notation? Well, we have seen this kind of thing before. This was in the prerequisite material and it was in a previous homework set. There is the interval notation for the same set. Now let's use set notation. The set of all x such that x is less than 3 or 7 is less than x. So notice I did not say the word and. I mean, you could describe this set informally as the set consists of two pieces, this piece over here and this piece over here. But when you describe this set using mathematical terminology, you say that the set is the union of two intervals, and you say in set notation, it's the set of all x that satisfy this or this. All right, now let's do question C. Solve the inequality f of x greater than or equal to 0 and present the solution set 3 ways. Well, let's go back up and look at our sign chart again. Realize that the answer to this question is going to be very similar to the answer to question B, except that we want to include these endpoints of these intervals. X equals 3 should be included because the y value 0 is greater than or equal to 0. And x equals 7 should be included because the y value 0 is greater than or equal to 0. So when I make a picture using the number line, it's going to be very similar. So there's my number line with those dots filled in to indicate that x equals 3 and x equals 7 are included in the solution set. The intervals are going to be what are called half-open intervals. And in set notation, the solution set looks like that. That's the end of that example. The next example, we're supposed to solve this inequality and present the solution set 3 ways. Well, notice that so far in this video, we've been talking about sign behavior of functions, whether they're positive or negative or 0. And we have a sign chart method for determining the sign behavior and presenting the sign behavior of functions. In this inequality, I have an inequality that compares two expressions, and it's not in a helpful form. A more helpful form is where you have an inequality comparing something to 0. So how would we get such an inequality? Well, we just rearrange this inequality. Now recognize that the left side of this inequality is a familiar function. This is our function f of x from the previous problem. So we're being asked to find the solution to the inequality f of x less than 0, where f of x is the previous problem, the function. Well, let's go back up and look at the sign chart that we made for f of x. The x values where f of x is less than 0 are in here. There's our answer presented in a picture using the number line. Now we need to present it in interval notation. There's our answer in interval notation, and in set notation this will be denoted That's the end of that example. Here's a similar example, example 3. Solve this inequality and present the solution set 3 ways. Well, I'm going to follow the same method of create an inequality involving something being compared to 0. So that would be done by just rearranging the given inequality. So there's an inequality where we compare a function to 0. Now notice that this is a function that's a polynomial function, so we can use our tools of sign charts to solve this inequality. First of all, we would need to find the partition numbers. And it helps to have a name for the function. Notice that when the inequality was presented, there was no function named in the presentation of the inequality. But it helps to rearrange the inequality and introduce a name for the function. So we need to study the sign behavior of this polynomial, g of x, so we need to make a sign chart for g of x. So our first job in making a sign chart is to find the partition numbers. So g of x is a polynomial, so there are no x values that cause g to be discontinuous. So we need to solve the equation g of x equals 0. So I'm going to turn this around. So in solving this equation, we factored, and we factored more. Now I'm going to note the partition numbers. They're x equals 0, x equals -7, and x equals 7. But before I do that, I'm going to rewrite this in a different order. That factorization is more useful. Now the partition numbers that correspond to those factors are x equals -7, x equals 0, and x equals 7. All right, so we've done step 1 of the procedure for making a sign chart. Let's go back up and look at the procedure again. So we've done step 1, finding all partition numbers. Now the next step is to plot the numbers on a real number line. Plot the partition numbers. So let's go down and do that. So there's our number line, and right away let's title this. That's something that, again, was not indicated in the book's instructions for making a sign chart, but I think it's very important. The other thing that's not mentioned in the book's instructions is the thing that I added to indicate the behavior of the function at the partition numbers. So that's step 2. Let's go back up and look at step 3. We have plotted the numbers. Now we're supposed to select test number in each interval and find the sign of the function at that test number. So there are my test numbers. Now let's compute the sign at each test number. So there are my signs at the test numbers, and we add the information to the sign chart by putting pluses and minuses along the whole intervals. So on this leftmost interval, we have a bunch of minus signs. And then we have an interval of all plus signs. And then an interval of all negative signs. And an interval of all plus signs. And our sign chart is done, so I'm going to circle it. And again, notice that the sign chart has a title, and I have the behavior at the partition numbers indicated. Now let's remind ourselves what we're doing here. Let's go back up. So our original job was to solve this inequality, and we turned that into solving this inequality. So we want to know when g of x is greater than 0. So we will present our solution set 3 ways, a picture using a number line, interval notation, and set notation. So there's our picture. Notice those open circles are not filled in because those points are not included. Now we need to describe this in interval notation and in set notation. A couple of things to notice about this example and the previous example. Notice that the most obvious place to choose a test number might be the x value that's right in the middle of an interval. Like, say, for instance, x equals 3 or 4 is in the middle of that interval. Why did I choose x equals 1 and x equals -1 for these test numbers? Well, notice what happens when you use as a sample number that is 1 unit away from a partition number. That test number was 1 unit away from 7. That sample number was 1 unit away from 0. That sample number was 1 unit away from 0. And this sample number was 1 unit away from -7. Look, in every one of these calculations, it turned out that one of the factors was the number 1 or -1. That's because in every one of these calculations, I'm taking a difference of an x value and a sample number, a partition number and a sample number, and they're 1 unit away, and so that particular term in the product turned out to be a simple one, 1 or -1. That's why I personally always simplify my sign charts by choosing test numbers, sample numbers, that are 1 unit away from one of the partition numbers. All right, that's the end of that example. I want to make a little remark here about a common incorrect solution to this example. So remember, how did this example start? We were supposed to solve an inequality. We're supposed to solve that inequality, x cubed greater than 49x. Here's a common incorrect solution. I'm going to write it in red. Here's this solution. It's as far as I'm going to go. Find the partition numbers first by solving this equation. Now, we did the same thing. We solved an equation to find the partition numbers, but we didn't quite do the same thing. We rearranged our equation to have a polynomial equaling 0. So we set up an equation where a polynomial equaled 0, and we factored and we solved that equation that way. In this current solution, we didn't do that. We just set up an equation and we solved that equation. And look, we're missing a partition number. So this is not the correct solution. So what went wrong? This seems like we did perfectly legitimate stuff. Why did we not get the correct solution? Well, the problem is in this step right here. This dividing by x, you can't do when x equals 0. So if you divide by x, you're basically saying, well, I'm assuming that x is not 0. And what we ended up with was we found all the solutions that were not 0. Well, when you do that, you might miss the solution x equals 0. If it turns out that x equals 0 was supposed to be one of your solutions, You won't find it using this method because there's this step that you do that basically assumes that x is not 0. So this whole solution is an incorrect solution. That's why I've written it in red. All right, that's the end of that example. Our last example is to solve this inequality and present the answer 3 ways. So we should take the same approach that we had in the previous problem, that is to identify a function that's involved in this problem, and then study the sign behavior of that function. So let's let our function be this thing that's over here on the left. We're going to let that be f of x. So there's our function. F of x is that rational function, and we're supposed to solve the inequality f of x less than 0. So let's make a sign chart for f of x. So step 1 is to identify the partition numbers. Well, we know that to find the partition numbers, it helps to factor the function. So we can identify the partition numbers clearly in this factored form of the rational function. We see that there are 2 x values that will cause the numerator to be 0. That will cause the y values to be 0. And there's 1 x value that will cause the denominator to be 0. That will cause the y value to be undefined. That will cause the function to be discontinuous. So there are our 3 partition numbers. All right, now let's move on to step 2. Make a number line and put the partition numbers on the number line. Now remember the additions that I suggest. Title the sign chart and put on the behavior at the partition numbers. At x equals 0, the y value is 0. At x equals 13, the y value is 0. And at x equals 17, the y value does not exist. Okay, step 3 is to determine the sign behavior in the intervals. Find test numbers and determine the sign behavior on these intervals. And there's our sign chart. Notice a couple of things. When I was computing my signs, I didn't even bother to find the values of these numbers. Because again, remember that we're just after this conclusion. Is the result positive or negative? So for that, we don't even need the values of these numbers. We just need to know whether the numbers are going to be positive or negative numbers. So here, it was enough to just know that I had 3 negative numbers being multiplied and divided. So the result was going to be a negative result. And again, remember that I titled the sign chart and I put the behavior at the partition numbers. All 3 of these things turn out are going to be important in finishing this problem. So now where are we? Remember, we're supposed to solve this inequality, f of x less than 0. So there's the sign chart. Now we need to present our solution to the inequality. So we need to present the solution to the inequality f of x less than 0. First of all, we'll do the picture involving the number line. Let's go up and look at the sign chart again. The places where the y values are less than 0 are these places here, these two green circled areas. So there's a picture of the solution set. Let's describe that using intervals, and let's describe it using set notation. There we go. Now, again, keep in mind that in the book exercises, you're only asked for a solution in interval notation. But I think it's helpful to draw a diagram, a picture that shows the solution set. Is a nice intermediate way between the sign chart and the solution for interval notation. All right, that's the end of that part of the example. Let's go to the next part. There's actually a question B. Question B is to solve this inequality. So remember, the inequality that we just solved was less than 0. So the inequality was that one. So what we're being asked to solve now is f of x less than or equal to 0. Well, we've already got the sign chart for the sign behavior of f. So let's just go up and look at that sign chart again. Here's the sign chart. The places where f of x is less than or equal to 0. Well, this time we're going to include that endpoint because the y value of 0 is less than or equal to 0. And we're going to include this endpoint because the y value of 0 is less than or equal to 0. But we're not going to include the endpoint of 17 because the y value of does not exist. Well, that's not a y value. We can't say that the y value at x equals 17 is less than 0 or less than or equal to 0 because there is no y value for that comparison to be made. So when we make our picture of the solution set, we have to be very careful. We have to include the endpoints x equals 0 and x equals 13, but not the endpoint x equals 17. So there's our picture. Now it's easy to convert that to interval notation. These are what are called half open intervals. Notice the endpoint x equals 0 is included, but the left side of that interval has a parentheses. And on this interval here, one side of the interval has a bracket, the other side has parentheses. Let's describe this in a set. So again, in your book and in the MyLab questions, you would only be asked for the interval notation. And in fact, in the MyLab questions and in the book questions, you tend to not get tricky questions like this where you have to pay close attention to the endpoints. You just get questions like the one we just did above, where we were solving an inequality that was a strict inequality. So that means that the endpoints are never going to be included, and so the answers always have parentheses in the interval notation. All of the intervals have parentheses. But it's unfortunate that the book only includes those kinds of examples because there are lots of inequalities that are not strict inequalities. Like this inequality is not a strict inequality. It's a less than or equal to, and its solution set is more complicated. And this is why it's important when you're making a sign chart to indicate the behavior at the partition numbers. When we made this sign chart, we included this information. That was crucial for solving question B, where we had an inequality that was less than or equal to. We actually had to pay careful attention to what was happening at the partition numbers. So that's the end of this example, and that's the end of the video. Thank you.